Right, so we continue with part 2 of this video. So we haven't finished yet. We just calculated the total head on the pump using the following equation. But the remaining is how we can determine the operating point for the pump in the system, which we have designed and given the performance parameters for the pump at the operating point. So they provide us with this table, and it's saying this table, the static head is when the pump is switched off, it's about 48.9. You'll say how they got this value. Very simple. Based on the equation, when is the pump switched off, there is no losses in the system. The system is static. So we have the delta Z plus P2 over gamma, difference in pressure or pressure head. H losses will be going away. So it will be only 24, I did the equation here, 24.4 plus 24.5, which is related to the pressure, and that the elevation head will give you 48.9. We call it the static head. Now you say, how can I develop these values? You bring here, kind of like, because you have a value here, you just change the Q, automatically everything will change for you. And if you change the diameters, then you need to update that with the diameters. So you can create multiple sheets to go through that scenario. So let's start with the question itself. But before that, I want to tell you, I selected one of the pumps earlier. I think we'll match it. And this pump, you read it as 2 times 3-10. 2 represent for me, the first number is the discharge connection size. 3 is the suction connection size, nominal in inch, and casing class, nominal size in inch, largest impeller. So it's moved from 6-inch to 10-inch. This graph is reading for me the capacity, liters per minute. So I'll tell you that is something as well. The question is giving us meters cubic per minute. I need to change it to liters per minute, but also I need to change it to cubic meters per seconds, because that's how my Excel file set up here. I'm working with SI system units, meter cubic per second. So that's something we'll work around. And here it's telling me those different impellers we work in diameters. The blue lines, the green lines representing the efficiency for the pump, the red lines representing the horsepower of the pump. Q is the volume flow rate. We're reading total head and as well net positive suction head required, which will be the third video for this series to cover the entire design. Here, I need to work within my liters per minute and the total head in meters. So I follow these dimensions based on that. And that's a bit tricky, but I'll show you how going through it. But what we're trying to do, based on my H values, applying from 0 till a certain number, I will get this curve, which we call it the system resistance curve. And I intersected with one of the suitable curves for the pumps. I think it's about 9-inch or 8-inch between them. And then I will determine based on that the operating point and as well the desire, the one they want me to do it. So one is the maximum point which the pump can work with no issues based on my pump curves and the efficiency for it. So that's what we're trying to achieve. So first of all, I converted this earlier in a graph here. So I'll put these values here for you to see them. I'll just organize them for you. Remember, you can tidy up always your Excel files and make them really nice. So that is the Q. I could change that to be Q meters cubic per second, and I'll tell you why very soon. Reason. So put that here, just brackets and the units, make that to be cubic superscript, and that is very simple. Equals to change that, you just divide it by 60. It's kind of like you're moving it from minutes to seconds. And as well, I need to change that to Q liters per minute, because you say, why are you doing that? Because technically that's how the graph is set up here, which is something. How do I do that? So it's that 1 times 1000, and you get the values in cubics per minute. So liters per minute. Now, the HA, which the one I'm trying to calculate, you have two options, but I'll talk about it in how you do it. So here it's the textbook is giving you, but it's actually something we could do it. Use subscript, and that way you make it nicely seen. So HA is very easy to obtain as long as you do the calculation correctly. So the first one would be equals, as you can see from the example, is 49. That's then the pressure is not dealing. And then here you will just substitute that value and you get this. So what I will put here equals to this value. And you say, that's not the right value. I'll tell you, yes, it's not the right value. And then you will, this value, you change it to match this value, the Q meters per second. And as soon as you get that, you get C now it generated for you at 49.6, and you go through the same equations. Of course, would be challenging to do it in a way without mapping that to the Excel sheet. So what I usually do, I copy that one here, and then I put the values so I can see them nicely. We can delete that cell because we don't need that. And here we can see it's 48. Sorry. It's just that one interfering with me. 48.9. And this one is 49.6. And then now to go to the second value, you select this value and you say, okay, let's go to the second flow rate. You select this, and then it comes to 51.52. And you go to select the third value. See, it's not difficult because I didn't use Moody chart formula, so that was easy for me. 54.57. So that is just telling you, in the textbook, they make life easy and they give you that table, but I'm showing you how that table can be generated. You just put the numbers to go from 0 to 1.1. Now, why they choose 1.1, or it's actually they're trying to match the capacity, the charts, or the things you're going through it. And you continue with that till you get the value. So to save time, I would choose their values at the moment. So that is just to save time, but I'm just showing you how you can do it in a simple way. So to save your time with it, just an example for if you ask me, how do I generate that table and how can you go through it? Okay, so I have Q and HA. Now I need to generate a chart. So insert, I select Q, volume flow rate, and HA, and insert, and will generate for me that nice curve. Now, there is a challenges here which I need to work with it. So first of all, put that chart here. I'll make some lines. So I will map my chart within the design they have. I copy from the textbooks. And my concern is like I'm not onto the scale, but I would do it as much as I can to make sure I get something really solid. So that will be my x-axis. If I want to increase format shape, increase the width of that so it's easy to see it, and then I'll bring another one to go through that point and make it as well and increase the width of that. So that way I'm kind of like trying to understand where is my point. Put some points here. That's the 4. So I'm just matching the 0 points and the 1,400s. That is very important because I'm trying to generate a graph to put on top of other graph. Okay, it's just for simplicity. And if I have another validity point in the middle, let's say the 600, and also I could put the other one, which is 850 around this point. So that is the 850. Why 850? Because that was given to us in the question initially. It's 850 liters per minute. Now that graph I got there, change that color to blue, and I could change the graph itself to make it size 14 as an example. The dots as well, we can change them, the markers, to blue. That way we can see it clearly. Change that scale to 140. I'm matching the graph, so 140. If the flow is starting from a certain value, so starting from 20, I would do that as well. Axis 20. Now it's very important when I do the lines here, Control C, Control V, I put the 20 here so I understand where is my point. So see, I'm removing this line. So it'll be between 20 and 40. And this one, I change the size, so starting from 0 to 1400. By the way, there are other software can do that, but I'm saying I don't have softwares at the moment, so how can I work with that? That if it's giving me negative, make sure it's really actually reading 0, because we want to set up that 0 point. So I always expand that to show the 0 line, and that's nicely. Expand that to make it really good. 1400, just show it. Make that like grid. Possibly show the 500s, so that way we can cut it. Yeah, and then say show 200s measure. That could, that will show me very nicely. Okay, make it that way. Now, if you look carefully, I could really cut the edges of this one and make those edges to be no fill. So in that way, I can make it transparent and no fill. So see, you can see through. And as well, I could just generate a color to be dark a bit so I can see through. And this one as well. Like it's just a bit of arrangement. You spend first time on it and then we'll be fine as well, the top one. So we can have it really nicely done in a way we can. All right, I think that's enough. So now you come and match it exactly on the boundary. So this is my 400 and this Control X, Control V, I'll put it on top so it can see my corners, and then bring the other one here to match it exactly with my boundary. Will not get you exactly the same, but that it's actually very nice and well organized in a way, so I don't have problems, and will be plus minus errors, but that should be fine for my design at the current moment. All right, so I got really that nice design for my values, which is really good, and it's showing it to me where they will intersect and how it's going through it. It's actually that point here. It's the one I'm looking for, and it looks like I'm in between it. So if that goes a bit slightly down, yes, and then I can get that point. So I'm matching the 40, the 20. You can see my scales reading 20 and 40, and here is reading just the 400s. Can come here. Need to make sure the 400s is the one who's reading. 400s. If it's difficult, you can always come to this section and select the lines, and then from there you can make X's, tick, and you can say outside. That would show me. So see, now I'm showing where it is exactly. So I need to bring that one to be on the 100, 1400, and this will be here is around 850. This is the 600, so I got it slightly. I'll move it a bit. Yes. Now looks like slightly. Yes, now it's came very precise. All right, so that is my the blue one represent for my curve. Now I will draw the line. So obviously the 9 inch is the right one. So what I will do, I will choose sharp and use that line. I'll start from here and then maybe not this line. Insert this one. Go insert this one better. And then you track the line which we are interested in, and then escape, and that one right click, format shape, change that shape to green, and then give it bigger. Oh, maybe green interferes with the original green, so give it maybe yellow. Not really. Choose something easy to distinguish. Purple is good. Increase the thickness is just to show it and going through it. So you have that. It's technically what representing for me based on what I explained. The blue line represent for me the SRC, which is the system resistant curve, which we calculating based on HA values based on the Q, based on the calculation changing the volume flow rates, and you generate that. Based on the intersection, I found my system is really lasting here, intersect. So it didn't go and intersect with that one. I could choose the 8 inch, but I avoided it. The question why I avoided the 8 inch, because the intersection, it's to call it the operating point, is actually at this point, which is less than 800 liters per minute. And that's not the question. They want us to deliver, the required to deliver is 850. So my operating point should be higher than that. So you see 850 here. So that is where is my delivering point. My operating point should be here. So if I add another line to show the operating point, I come to shapes and I will choose something with arrow. So the intersection is technically this point. I will make it really distinguish color, format shape. So that we call it the operating point. And I'll put just a brackets here. I'll call it operating point. Okay, so that is my operating point. Is obviously it's bigger than what I needed, and my 850 represents here. The 850 is the desired point. So 850 liters per minute is the desired point. Okay, so my pump, the one I selected in this example, it's giving me really better than, don't move it, because if you move it, we ruin this. We're giving me better performance. Now I can read the values. So I'm about an efficiency between 57 and 56 is close to 56.8. So efficiency is 56.8. The horsepower, it's about 30 to 40, so I would say that one is going around 34 horsepower. And based on that as well, I can go to 3 inch and see another value we could read. Insert is the 9 inch impeller. I will read towards that point, the net positive section head. Make that one maybe blue. That will read for me the net positive section head designed by the pump, which is required for us, which is something I will do and explain for you how to calculate, because that is the required, but we need to know how much is available. So that was coming from what? The intersection of this line with the 9 inch and you go and read from there. Make sure to read the meters, not the feet, otherwise you'll be in different scale. So it's about 3 meters is required. So we need to know how much is available, but when we go through it. Now, I've done this. Now, if I want to show this in more organized style and something easy to see, but it's good to show that's the operating and desiring point, how you go through it. Remember, it started at this point, which is 48.9. We call it the H naught, which is the static head force system, as you can see it from this diagram. And the one where it's coming here, you read it from that point. It's the operating point, which is technically reading for me the, what we call it, the actual total head on the pump when you run it with that pump. And then the remaining you go through it, and this is the information you get from the chart. Now, sometimes what I do to make life easy for me, I duplicate that, say copy, move, or copy. I say copy and create that size. And then when I copy that one, I like to show this in a nice way. And now you can see my pump and desire all, and I can remove the lines, and I just put the thing. So to go and read the actual is actually you bring another line coming from this point, intersecting between them, and that is actually reading for me the H actual, HAC. It's above 80, between 80 and 100, so it's around what it's giving to me for that pump I selected. That is just to show you how the graph, and by the way, you can label and make it really nicely and based on it. But see the points I try to match. The 1400 is the line, perfect. The 600, remember, it's okay sliding because it's the scale, but that's where it's going through it, and that's what I wanted to ensure my scale is working exactly. The 120 and the 140, see when I remove the previous diagram, which I didn't delete here, I had a copy, to make sure I map them really nicely and I didn't create any issues. So that is the question about finding the relative information for this design question. Now, after that, the third video will be talking about calculating the net positive section head required. See you with the next video.